Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are just going to evaluate this crazy integral. And you know what? What like integral evaluates to a fascinating and amazing result. Do you want to see that result earlier or do you want to see that result right now? Okay, wait a second. Let me just show that to you. So this is the result that we will be evaluating this to. So basically this integral evaluates to g over 2 minus 3 over 16 times Riemann zeta of 2. And basically, or you can say that Riemann zeta of 2, we know that it's pi squared over 6. And again, if you are not familiar with this, so you can just consider watching my video on Riemann zeta of 2. I have evaluated this using Fourier series. So if you are not familiar with this, please consider watching that video and then just come back to this. And when you plug here pi squared over 6, so basically this evaluates to g over 2 minus it's pi squared over 32. So this integral evaluates to this, and what's g here? So g is Catalans constant. Actually, basically it's an infinite sum that looks something like this. It's going from k equals 0 to infinity of -1 to the k over 2k plus 1 whole squared. So this is g. This is Catalan's constant. This infinite sum known as Catalan's constant, which is being represented with z. I'm sorry, not z, but with g, right? Okay. Now I think it's this integral is not easy to evaluate at all. So without any kind of wasting our time, let's begin the evaluation or the formulation for this integral. Okay, so basically let me tell you something right over here. Wherever you see something like logarithm or natural logarithm inside an integrand, and if your limits are from 1 to infinity, and again if you got something this type of thing, so without any kind of thinking or anything else, you just have to let x equals 1 over t straightforward. This is your first step here, and I'll show you how does this works. And basically when we take about the dx derivative, so it's -1 over t squared and dt. And if we talk about the limits, so when you plug infinity here, so 1 over infinity tends to 0, so basically infinity will tends to 0. And if we plug 1 here, I'm sorry, oh wait a second, I have to care about x here, I'm sorry. So t is 1 over x. So when you plug x equals infinity, so 1 over infinity is 0, right? Actually tending to 0, not exact 0. And 1 over 1 is 1, right? So basically 1 is goes to 1. Okay, so now we are good to go with our substitution here. I think I should just plug this here a little bit, and then I would, firstly I should consider this as I. And then our I is integral from 1 to infinity of ln x over x plus 1 times x square plus 1 dx. So from substitution or from assumption, we can say that it is integral from 1 to 0, right? And ln of 1 over t over it's 1 over t plus 1 times 1 over t square plus 1, and then it's negative dt over t squared. Again this negative is here to fix this bounds because it's not properly bounded, so we would be using that to bound, and again to fix that bound. And this is a negative of ln t, so basically we can write our I as after just fixing bounds and a negative from the ln term, we would be having ln t over it's 1 plus t over t and times 1 plus t squared over t squared and dt over t squared. So basically we can see this t squared cancels out with this one, and this one would be come up to denominator, I'm sorry, numerator. So basically we're having negative integral from 0 to 1 of I'm sorry, t ln t over it's 1 plus t and times 1 plus t squared dt. Okay, so from now onwards we are just going to work on this integral. Okay, so I'm just going to work on this integral like this one. Just have a look at this. I'm just going to multiply and divide with 2 here. So 2t over 1 plus t times 1 plus t squared. Oh, don't worry, I have not forgotten the ln t here. I'm just writing it as something like there, right? Okay, so now you know what, why I just multiplied and divided with 2 here, because in order to get something here, if we talk about 1 plus t whole squared minus 1 plus t squared, so basically this is 1 plus 2t plus t squared, right? And this is minus 1 minus t squared. So this minus t squared cancels out with this one, and this positive one is cancelled out with this one. So basically we're having 2t. So that is why we can write 2t in terms of this one. And then something crazy is going to be happen. Just wait for that. So it's negative 1/2 integral from 0 to 1. We can write the numerator as 1 plus t whole squared minus 1 plus t squared over 1 plus t times 1 plus t squared and ln t dt. We don't have to forget about ln t, because that is why this integral is difficult. Otherwise it's not that difficult, because if you look here, so if we remove ln t, or we have to change the limits obviously, because it's a polynomial integral. So I'm not sure, yeah, but it's not like that. But if it was this function only, so this limits would be fine, but I have to check for this one. But if we remove this ln of x from here, so it's just a basic integral of like fraction by parts, I'm sorry, partial fractions. So that is quite easy to evaluate, right? But it's not like that. Ln is introduced to make this integral tougher or difficult. Okay, now we can just split this into two separate things, something like this one, and the another one would be this one. Okay, so now onwards we are just going to do 1 plus t whole squared over 1 plus t times 1 plus t squared minus 1 plus t squared over it's 1 plus t times 1 plus t squared and whole times ln t dt. Okay, fine. Well, it's 1 plus it's 1 plus t and it's 1 plus t squared. So a factor would be cancelled out with the another factor of this one. So we would be just left with 1 plus t in the numerator, and we would be left with this one in the denominator as well. So I is basically 1 over 2 integral from 0 to 1. It's 1 plus t over 1 plus t squared we are left with. And if we talk about this one, so this is fully getting cancelled out, and we are just left with 1 plus t here, ln t dt. Okay, now I'm just going to multiply this negative into this parenthesis in order to get a reverse order of this. I'm sorry, this would be come up here, and this would be in a negative sign come up here. So let's do that here right away. So it's 1 over 2 integral from 0 to 1, 1 over 1 plus t minus 1 plus t over 1 plus t squared and ln t dt. Okay, so now till now it's totally fine, but what next? Because we ain't having something like easier things in it, so we just have to, now we are good to go with dealing with this one and this one. And how so? So basically we know that 1 over 1 plus t is the sum as k goes from 0 to infinity of negative 1 to the k times t to the k. It's an infinite geometric series, right? And you need to care about this. I have used this multiple times in my videos. So yeah, if you are a daily watcher of my videos, so you might be following this. And if we talk about 1 over 1 plus t square as well, so it is, yeah, k goes from 0 to infinity of negative 1 to the k t to the 2k. So this is what we are just going to plug into our in the place of like this one and this one. So we would be having some infinite series as inside our integrand, and then we let's see what is happening. And be careful that this is a factor, so don't forget about this one. So basically I comes out to be 1 over 2 integral from 0 to 1. And if we introduce our first geometric series, that is this one, so we would be having on the place of 1 over 1 plus t infinite series as k goes from 0 to infinity of negative 1 to the k t to the k, and then with a negative 1 plus t factor, this sum as k goes from 0 to infinity of negative 1 to the k t to the 2k. And yeah, it's fine. And ln t, again we don't have to forget about that. And now I'm just going to expand, like I'm just going to multiply this one with this one and then this one with this one, so in order to get three infinite series inside our integrand. So basically we would be having I equals 1 over 2 integral from 0 to 1. So first infinite sum is as it is, that is k goes from 0 to infinity of negative 1 to the k t to the k. Second would be negative 1 times, actually, so it's k goes from 0 to infinity of the same function t to the 2k. And then look, this t actually negative factored out actually, so let me just plug a negative sign here. So this t would be just getting like multiplied with this one, so in order to get t to the k plus 1, right? So basically we are having k goes from 0 to infinity of negative 1 to the k t to the k plus 1, and this whole times ln of t dt, right? Okay, now what I'm gonna do next, I'm just going to multiply this integral in all these three things. So let's do that here. So I comes out to be 1 over 2 integral from 0 to 1 the sum as k goes from 0 to infinity of negative 1 to the k t to the k dt. Oh, wait a second, I just forget about the ln t here, because that was also a factor, we need to care about that even. Negative 1 over 2 integral from 0 to 1 the sum as k goes from 0 to infinity of negative 1 to the k t to the 2k ln t dt, right? And finally the last term, integral from negative 1 over 2 integral from 0 to 1 of this sum as k goes from 0 to infinity of negative 1 to the k t to the 2k plus 1 ln t dt. Okay, now since from linearity we can say all these three things are gonna interchange their positions, and since this negative 1 to the k in all terms are independent of x, so that would be also out of the integral part. So basically we are having I equals 1 over 2 the sum as k goes from 0 to infinity of negative 1 to the k integral from 0 to 1 t to the k ln t dt. Next 1 over 2 the sum as k goes from 0 to infinity of negative 1 to the k integral from 0 to 1 t to the k ln t dt. Fine. Okay, next 1 over 2 the sum as k goes from 0 to infinity of negative 1 to the k integral from 0 to 1 of t to the k plus 1 and times ln t dt. Okay, so finally we are having this kind of things here. Now we have to care about this integral, and this integral separately actually. So let's talk about them separately. So let me consider them as the first integral. I1 equals integral from 0 to 1 t to the k ln t dt. So for this I'm just going to use the famous DI method that I have been using in most of my videos, in which we need for by parts, or maybe all of my videos, because that the standard way is quite boring and something I don't like this personally. So that is why I like this one, and this is quite efficient. Okay, so taking the different derivative of ln t and integrating t to the k. So it's 1 over t and it's t to the k plus 1 over k plus 1. So this times that, and this is inside an integral. So if we talk about I1, so it's ln t times t to the k plus 1 over k plus 1, evaluating from 0 to 1, and minus 1 over k plus 1 as a factor integral from 0 to 1. If we combine this one with this one, so we're gonna have this power would be cancelled out, and we would be having t to the k here dt, right? And if we talk about this here, so when you plug 1 on the place of t, so it's ln of 1 is 0. So first 1 is 0, right? And if we talk about 0, so 0 here, so it's totally 0. So basically this is going to 0, and we are having I1 equals negative 1 over k plus 1. And if we integrate this one, so it is giving us t to the k plus 1 over k plus 1, evaluating from 0 to 1. So basically we are having I1 as negative 1 over k plus 1 whole squared. So again, interesting thing. And similarly we can evaluate this integral as well as this one also. So let's evaluate them separately, but I thought to just leave this for you guys, but it's all right. You can just pause the video right here to evaluate those integrals by your own. But yeah, if you do that, so that's a good thing. So I'm considering I2 equals integral from 0 to 1 t to the k 2k times ln t dt. So again using DI method, so it's ln t 1 over t to the 2k, it's t to the cube 2k plus 1. And yeah, so basically again this part ln t times t to the 2k plus 1 over 2k plus 1. I'm sorry, it's 2k plus 1. Please just care about the factor I just missed here. And this again evaluates to 0 finally, and we are left with negative 1 over 2k plus 1 integral from 0 to 1 of t to the 2k dt. And again we are when you evaluate this thoroughly, so we are gonna have this I2 equals negative 1 over 2k plus 1 whole squared. And similarly I'm not gonna do the third one, I'm just leaving it for you. So similarly I3 is negative 1 over 2k plus 2 whole square. It's a guess, and yeah, it's correct. So now we are just going to plug back into our I1, I2 and I3 into our this expression here. So now we would be having something crazy. Let's just plug them back, and now let's just do that right here. So basically we are having, I think I should just copy that down here a little bit, because it's quite difficult to just remember them all at once. Oh, I'm sorry guys, wait a second. Okay, so yeah, I have copied them here. I'm just going to paste them here, and yeah, oh wait a second, what happened? Oh my god, what's okay, here it is. Yep, now let's just plug them back. So I equals 1 over 2 this sum as k goes from 0 to infinity of negative 1 to the k, and this evaluated as 1 over k plus 1 whole squared, right? Let me check that once. Yeah, okay, And now if we talk about the second one, so it's this sum as k goes from 0 to infinity of negative 1 to the k, and it was evaluated at 1 over 2k plus 1 whole squared. And finally this one 1 over 2, this sum as k goes from 0 to infinity of negative 1 to the k, and times negative 1 over 2k plus 2 whole squared. Okay, so now let me just rearrange them a little bit, and then we would be having some better results. Don't worry about that, I'm here. So yeah, it's, oh, I'm sorry, I think I should have taken a factor of negative half here, because look, this negative one is being factored out here, and again so for the all these terms, so basically this is going to be positive and this one also going to be positive. So let's just do that carefully here. So we are having negative 1 to the k over k plus 1 whole squared, right? Next 1 over 2, the sum as k goes from 0 to infinity of negative 1 to the k over 2k plus 1 whole squared. Do you remember, guys? This was our Catalans constant that I just talked about it in the beginning of the video. So this is Catalans constant, which is g. So from now onwards I'm just going to represent this infinite sum as g, and you know what, there was a factor of half in front of g, so basically we are having the first part of our result and we are just going for this one. Don't worry, that is that everything, let me just show you that this everything, I'm sorry, this everything and this one also going to be evaluated to negative 3 over 16, I'm sorry, yeah, negative 3 over 16 zeta of 2, Riemann zeta of 2 actually, and again a positive 1 half the sum as k goes from 0 to infinity of negative 1 to the k. Well, we can do this as 2k plus 1 and whole squared. Actually inside that parenthesis I've just taken out 2 common because we can do that in order to get, you know what, in order to get this one and this one result equal, and that I'm just gonna do them in a single series because they are having same functions in it. Oh, I'll show you in a later, in a while, don't worry about that. So we are having negative 1 over 2. Oh, here if I'm just going to replace k plus 1 with k here, so I have to just begin our like, I'm sorry, this sum from k equals 1, right? Actually I don't like this k plus 1 in the denominator, so I just have to convert this into k. So in order to do that I have to just begin our infinite sum from 1 itself, and this would be k minus 1, right? Well, you can think about that, that's not a difficult thing at all, you can think about that by your own. I'm just going to just replace here, basically I'm just going to replace k plus 1 with k here, but that's it. And yeah, so basically we are having the sum as k goes from 1 to infinity, don't be confused here, from 0 when we were having k plus 1 in the denominator, so our series was beginning from 0. But when I'm just talking about k in the denominator as a factor, so I'm sorry, as a function, so I have to begin our series from k equals 1, and this would be negative 1 to the k minus 1 over k squared, and this is 1 over 2 times the Catalans constant and plus 1 over 2, and since this is a 2 squared, right, so basically it's 4, so I can just factor that out because that was a constant, and this is, again I'm doing the same thing as I did for the first sum to this third sum also. I'm sorry, I should be writing it that from 0 to 1, but from k equals 1 to infinity. So again this is negative 1 to the k minus 1 and it's k squared. So now you can think of that we can just combine this one and this one both in at once. So basically again we are just leaving something negative 1 over 2, or I can write this as 4 4 over 8, the sum as k goes from 1 to infinity of negative 1 to the k minus 1 over k squared, and this is 1 over 8, the sum as k goes from 1 to infinity of negative 1 to the k minus 1 over k squared, and don't forget about this Catalans constant over 2. So now we can just combine them, and we would be having when we talk about this plus this, so it's negative 3 over 8, right? So negative 3 over 8 times the sum as k goes from 1 to infinity of negative 1 to the k minus 1 over k squared plus g over 2. Okay, so now we are just going to play a little bit with this sum, right? Because we are just getting disturbed with this one. If it is 1, so we would be having the Riemann Zeta of 2, but still it's not 1, so we have to just do some manipulations, or manipulations and some changes in it, so in order to get the Riemann Zeta of 2, because we are not here to find Riemann Zeta of 2, but after solving it we would be have Zeta of 2, right? So let's just solve it down. Well, I can write this as, when let's expand this further, let's expand it a little bit. So when k equals 1, it's 1, right? When k equals 2, it's 1 over k squared, right? I'm sorry, 1 over 2 squared. And when k equals 3, it's plus 1 over 3 squared plus 1 over 4, I'm sorry, it's a negative, so yeah, and plus 1 over 5 square minus dot 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 to infinity, and plus g over 2. Okay, now what I can do here, I can just talk about the even reciprocals squared and the odd reciprocals squared. So basically I'm talking about this negative 3 over 8 times 1 plus 1 plus 3 squared, 1 over 3 square plus 1 over 5 square dot 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 to infinity. And if we talk about the even reciprocals like this one and 6, so we are having a negative in front of all them, so let's take common this out, and that would be a positive 3 over 8, and that's 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, and dot 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 to infinity, and don't forget about the g over 2. Okay, now okay, so basically okay, so now what we are going to do is let's just do again a manipulation for this one. And what's that? So that is, let's talk about this one here, 1 over 3 square, 1 over 5 squared, and dot 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 to infinity. And well, we can write this as negative 3 over 8, 1 over 2 squared, 1 over 4 squared, dot 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 to infinity. And in order to get this result back, I have to just add this with 6 over 8 factor of this same sum, right? Because when you solve these two things, so you're gonna have this result only, right? So like why I did that, you will get to know in a while, don't worry. And now I'm just going to combine these two things, because their factor, my negative 3 over 8 is common here, and so that is why we can add them up together. Negative 3 over 8, 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared dot 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 to infinity. And you know what, here we are with the Riemann Zeta of 2, our first Riemann Zeta of 2, and we can cancel this with 2 here, so we would be having 3 over 4, the sum 2 squared 1 over 4 squared dot 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 to infinity, and plus g over 2. So this is our Riemann Zeta of 2. So let's just replace that with Riemann Zeta of 2 here. So it's negative 3 over 8 times the Riemann Zeta of 2. Okay, and now it's fine. And now if we talk about this one, so we can plug a factor of 1 over 2 squared from each term to infinity here. So I'm having it's 1 plus 1 over 2 squared plus 1 over 3 squared dot 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 to infinity, right? And plus g over 2. Oh, wait a second, I just messed here. I think I should just write that down once more on the next page. So basically, like till now you're good to go with Riemann Zeta of 2, right? And next I'm just going to play around with this one, and what I'm gonna do there with that, it's negative 3 over 8 Riemann Zeta of 2. Well, since this 1 over 2 squares is can be factored out from each term up to infinity, so let's just do that. So basically we are having 3 over 4 and 1 over 2 square is 1 over 4, and when we factor that out we're gonna have 1 plus 1 over 2 square, so 6 square would be factored out 1 over 3 square and dot 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 to infinity. Hence we are having again a Riemann Zeta of 2 here, as you might see here. So we are very close to our result, guys. Okay. Oh, I'm really sorry, guys. Actually my tablet is on a notification mode, so you got to just this you got to listen 2 times of beep of notifications. I'm really sorry about that. Okay, so now we are having 3 over 8 Riemann Zeta of 2, and this is 3 over 4 times 4 is 16, and again it's a Riemann Zeta of 2 plus g over 8. Now we can just multiply this with 2 and divide this with 2. So basically we can write this as 6 over 16. So we can just combine them both. Actually we can just combine these two things because the denominator is same. So we're gonna have negative 3 over 8, negative 3 over 16 times Riemann Zeta of 2 plus g over 2. And hence we are here with our final result that I evaluates to g over 2 minus 3 over 16 Riemann Zeta of 2. And we can, if we plug this with pi squared over 6 here, so we're gonna have I equals g over 2 minus pi squared over 32. Isn't that amazing, guys? And we got to learn a lot of things from here because we did use of infinite sums, geometric infinite series, and a lot of things. Let me just do a little bit. So yeah, we are here. This is being proven. And yeah, that was really amazing journey, guys, because we did use of a lot of things. Like, let me just go through once here. So we did started with this substitution, right? And then we got to have from here to here, and then we did use of infinite geometric series 2 times, and then we got to have 3 infinite sums in it as an integrand, and then we are having this kind of thing here. So then we just integrate these 3 things. Actually separately we integrated them using by parts actually, and yeah, that was really easy integral. We just use this kind of things easily. That can be done easily. And then we just plugged the results in it, and we had where it is, this was the Catalans constant, actually half times Catalans constant. And then we did solve of this one, and then we did got a lot of things like this one. We did manipulations and we did a lot of things in order to get our final result, and that was really fine. So yeah, thank you so much for watching this video, guys. If you got to learn something, please make sure to like, subscribe and share. And if you got to have any kind of doubt in this video from wherever, you can freely ask me in the comment section. I'll make sure to answer that as fast as possible. So yeah, goodbye, guys, take care. And yeah, I'm just going to bring a very fascinating and amazing video for you guys. Just stay tuned for the next video, because some of my upcoming videos are really amazing and like beasty things. And yeah, the next video is gonna be amazing. Just be stay tuned for the next video. Thank you so much thank you so much, guys. Be careful, and yeah, I love you guys. Goodbye.